In this video, I want to explain some core Rust concepts by walking through a real project instead of a toy example. The code we're looking at is a crash-proof file pipeline. Its job is simple on the surface. It watches an inbox or a specified folder, takes the files, compresses them, hashes them, moves them into an outbox, and records progress in an SQLite database. But what makes this interesting is that if the program crashes halfway through, it can recover and continue without duplicating work. That design gives us a great way to talk about how Rust handles ownership, enums, pattern matching, error handling, concurrency, and stateful program design. So instead of asking what is a struct in the abstract, we can ask, why is this struct useful here? Instead of talking about enums like a textbook, we can show you how enums are powering the pipeline's recovery logic. Now, let's start at the entry point. Alright, I'll drop this down. Make myself smaller real quick. Alright, so we're at the entry point. And so this is basically where all the crates are assembled together in our Rust app, basically. And as you can see, we have so main wires together the CLI, database migrations, startup reconciliation, watcher thread, and worker threads that actually process the files. As you can see at the top here, we have some libraries or crates that are being imported. And so we have our, standard library right here. That's useSTD. And these are all the dependencies that our program relies on. And this is all the code that everything's going to be built on top of, basically. So, and then as you can see a little bit lower, we have our crash pipe library. And these are actually the files that we create right here ourselves. So we actually have access to this code. So we can control what's inside of these. And I'll go through each of these and explain all that. And this actually makes all this possible here, right? The library entry point for the crash pipe crate. So this file simply re-exports the project modules so the binary can use them through crash pipe paths. As you can see, it's crash pipe and 2 colons. And then because of this lib.rs, we can use all of our different, whatever functions we have in these libraries, or enums, or structs, or all the different Rust goodies that we have access to. That's all contained in this little section of code right here. But I'll explain more about that later on, so I'm kind of rambling a little bit. Alright, so in main.rs, the program parses command line arguments into a CLI struct. It initializes logging, creates the inbox and outbox directories, opens the database. It runs migrations, builds a pipeline object, scans existing files, reconciles old state, optionally starts a watcher thread, and then spins up worker threads. That is a very Rust-style main. It wires things together cleanly, pushes real logic into modules, and returns a results function so errors can bubble up naturally. And that leads us to the first big concept. So we have this right here, results, and the question mark operator. Alright, so one of the first Rust ideas people run into is the result type. In this project, main returns result, and throughout the code you see a question mark in a lot of spots, like right here. You got question marks, and now they've all been highlighted here. And that operator means if this operation succeeds, keep going. If it fails, return the error immediately. And for example, when the code creates directories, opens a database, or runs migrations, it doesn't manually write huge match statements every time. It just uses the question mark operator. And that keeps the code readable while still being explicit about failure. Alright, this is one of Rust's biggest strengths. Error handling is not hidden. It's part of the type system. A function that can fail says so in its signature. So basically, if you see this little question mark, it's saying that error handling is a part of the function. Alright, so moving on. And in your project, that matters because this is not throwaway code. If a database update fails or a file system operation fails, the whole point of the program is to respond safely. So, a nice way to explain result here is Rust forces reliability into the function signature. All right. And so this is your main right here. We can go ahead and scan through it. I'll put all this code on GitHub as well, so you can check it out at your own pace. And it's got plenty of comments in there, so you can see what it's doing, and you can add to it. So this would be a good program if you needed to create a local backup program. If you didn't want to rely on the cloud, you know. I mean, there's plenty of cloud services that want to charge you all kinds of money for, storing more stuff on their cloud. So, I mean, this is a way if you just had everything backed up to an external hard drive, you could run this program. It'll scan a file, and then it'll output it to the whatever path you specify. And we're going to go through that here coming up next. All right, so now let's look at structs. Structs. The Rust structs are how you group related data together. In this project, there are several good examples. You have a pipeline config struct holding things like the outbox path. Let's pull this up. Pipeline config struct. Here we go. All right, so this is a struct. Struct. I don't know if I'm pronouncing it correctly or all the way. Struct. All right, that's tricky. So you have a pipeline config struct holding things like the outbox path, lock timeout, and optional fail point. And that's this right here. And then you have the pipeline struct itself, which contains a database and the config. That gives you an object like unit without needing inheritance or class hierarchies. You also have a file record struct in the database layer. That struct represents one tracked file in the pipeline, ingest ID, source path, status, current step, attempt count, hash, output paths, timestamps, lock info, and error info. Okay, so that's a whole mouthful right there. But that's basically what this pipeline crate is doing for us. And by the way, each of these is considered a crate in Rust. You can call these a crate, and then together it's all a package. And I should probably go over our cargo.toml as well. Now here's the dependencies. Most of these are from the standard library, like anyhow and clap, and I should probably put some comments in here explaining what each of these actually does, but some of them are self-explanatory, like SHA-2, that's for hashing your files. Temp file creates temp file, obviously, I'm assuming, basically. And so yeah, your cargo.toml is going to have your package name, which in this case is crash pipe. That's the same as our folder name. It's going to have a version, edition, and then it's going to list all our dependencies. So when we run cargo build, it's going to automatically download all of this code for us and with the correct version numbers each time. So that way, if the version numbers change, it'll still pull the correct code. All right. So moving on back to where we're at with structs. I kind of got off topic there. All right. So you also have a file record struct in the database layer. Let's see, where's this file record struct? File record, reconcile record, file exists. Okay. So this is a bunch of logic that basically goes through each file, checks the records, checks to see if it exists already. If it doesn't, it's going to copy it. And process claimed. Okay. And I'm also looking for a file record struct. I should probably just search for this file record. All right. There we go. Use crate db. So the file record struct is actually in db. Okay. File record. Where are we at? Here we go. Here's our file record struct. Alright, so that struct represents one tracked file in the pipeline and just ID, and I believe I said that already. Okay. So in Rust, structs are usually plain data containers with strongly typed fields, and then impl. Do I have an impl in here? Impl. Yes, impl. Alright, so impl blocks attach behavior to them. Impl blocks attach behavior to your structs. Okay. So a struct is usually just a plain data container with strongly typed fields, and then your impl blocks attach the behavior to your struct. Okay. So, got our file record. Let's go back to file record. Our file record struct. Okay, so this is basically just all our data. It's basically a data container, essentially. I guess that's a simple way to put this here. As you can see, we have some strings. We have a pipeline status. We got an integer 64 base 64 integer. I'm assuming that's what I64 means. All right. Now, then we got some debug error logic. And also, all of our logic exists outside of main. Main just wires all of our crates together. And all the logic is actually in all of these other crates. Alright, so we have our pipeline crate. And then we have our database crate, which contains logic to fill in the database and access the file records inside the database. That's part of this program. Alright, so Rust structs let us model the system directly. Pipeline config models configuration. Pipeline models the running pipeline. File record models one database row representing one file moving through the system. That is much more concrete than saying a struct is like a class but without methods, which is technically incomplete and not very helpful, apparently. Alright, so I'll go with that. Alright, now enums, that brings us to enums. Enums as a state machine. This project has one of the best beginner-friendly real examples of enums, the pipeline state machine. All right, in state.rs, let's jump over to state.rs. All right, shared enums that describe pipeline progress. These enums are stored as strings in SQLite and used by the worker logic to decide what has already happened and what still needs to happen. So, in state.rs, you define pipeline status with variants like queued, processing, done, and failed. Then you define pipeline step with variants like queued, compressing, compressed, hashing, hashed, moving, moved, recording, and done. This is huge. Alright, a lot of beginner Rust content shows enums with silly examples like dog, cat, bird. Your project shows the real power of enums. They let you encode valid program states in a way the compiler understands. This is not just data, this is control logic. Alright, control logic. So, I have an enum right here. As you can see, there's no cat or dog or bird or animal in this enum. It's in something we can actually do something with. Something that actually makes a little bit of sense. All right, queued, processing, done, and failed. All right, those are 4 things we could probably understand. All right, queued, processing, done, failed. That's our pipeline status enum. And then we got an impl, which binds all the logic to our data container. And so we got some double colons, and so that's how you write your function. Now, I'm not going to go into exactly what all this, I'm not going to go into a deep dive on every line, but I'm just going to try to explain this on a surface level here. So in the pipeline code, decisions are made based on those enum values. For example, if the job is still at or before the compress stage, or if the temp file is missing, the program knows it needs to run compression. If the final output already exists, it can skip work and mark the job done. If startup reconciliation sees a temp file during the moving phase, it knows it can resume safely. Alright. Rust enums are not just labels. In this project, they are the backbone of crash recovery. Alright. Also, because your pipeline step derives partial ORed and ORed, you can compare steps directly. That's a very rusty design choice. Instead of inventing magic numbers for states, you let the enum ordering express the workflow. Alright, so the enum ordering is expressing the workflow. Alright, so let me jump up to my enum. Alright, so yeah, basically, this is the workflow right here, and it's all laid out in the code. Queued, compressing, compressed, hashing, hashed, moving, moved, recording, done. Alright, pretty simple. Records each step of the way. So if it gets interrupted somewhere, it knows, okay, it was in the middle of compressing, so it needs to restart from that particular step. Or if it goes all the way to the end, it's like, okay, it's moved, but it hasn't recorded. All it needs to do is just start recording. That way it's not starting from the very first step. So as you can see, it's doing a bunch of different steps. And you can also modify this code to have it do some other steps or remove some of these steps. Either way, feed it to your coding agent and it can whip it out for you pretty quickly. And like I said, all this code will be available on GitHub. And if you're liking this so far, go ahead and subscribe, like and subscribe. And we're almost through here. All right. So pattern matching and expressive control flow. Rust's match and if-let features show up everywhere in this code. Nice example is when the pipeline checks whether a hash already exists. It asks the database for the current record, then uses if-let sum existing equals to reuse the stored hash if it's already there. Otherwise, it computes a new one. Alright, so let's see here. So it asks the database for current record. And where does it do that? Alright, let's check out scan and queue. Okay, here we go. So for entry and file system, read directory inbox. And then it's got this little question mark, so if it fails, it's going to handle the error for us. And that lets us know that it might fail on this step as well. So that's a nice little, that's what this question mark's there for. It's like questioning whether it's going to work or not. So if you're not sure your Rust code's going to work, maybe you should add some more question marks to your statements. All right. And moving on, I'm just rambling again. All right. So a nice example is when the pipeline checks whether a hash already exists. It asks the database for the current record, then uses if-let sum existing to reuse the stored hash if it's already there, otherwise it computes a new one. So that's what it's doing in this code, and I just read that again. All right. That shows a very important Rust idea. Option forces you to handle absence explicitly. Explicitly? Yeah. In many languages, a missing value becomes null, and null becomes a runtime bug later. In Rust, option T makes that possibility part of the type. Okay. Sounds nice. You can explain it like this. If a value might not exist, Rust makes you say that up front. Then it gives you tools like match and if-let so you can handle both cases cleanly. The fail-if function is another great example. It uses pattern matching with matches, ! To compare a configured fail point against the current pipeline step. That is expressive, compact, and type safe. So this project is a good demonstration that Rust control flow is often more readable than people expect. It can look strict at first, but once the types are meaningful, the logic becomes very clear. Alright, ownership and RAII with temp files. Now we get to one of the most Rust-specific and most powerful ideas in your code, ownership and RAII. So in fsops.rs, that's file system ops.rs, there is a temp artifact struct. Temp artifact. There we are. Temp artifact struct and the impl, which binds all our logic to that data container, which is the struct. Okay. It stores a path and a committed flag. When you create it, it is uncommitted. When you call commit, it renames the temp file into the file path and marks it committed. But the really important part is the drop implementation. If the object goes out of scope without being committed, Rust automatically removes the temp file. Alright, so this object owns the temporary file. If the program finishes the move successfully, it commits it. If not, Rust automatically cleans up when the object is dropped. That is RAII. Resource acquisition is initialization. The lifetime of the resource is tied to the lifetime of the object. In a lot of languages, cleanup is easy to forget. Here, the cleanup behavior is attached directly to ownership. And in the pipeline, you use it like this. Create a temp artifact, and then call commit to atomically rename the temp file into place. If something goes wrong before commit, the drop logic handles cleanup. That's one of the strongest Rust superpower moments in the project. Alright. Well, that's nice. Let me go and start this real quick. I actually made this little website to try to explain this as well, which I haven't been using this whole time, but I think I'm going to switch over here. So where we're at, ownership and drop. I think that's what we just explained. Yep, temp artifact. Okay. This actually looks a little bit better. I guess I should have been using this the whole time, huh? Alright, so I'm going to explain this again. So file system ops.rs. And like I said, the code is on GitHub in case you want to check it out on your own or while you're watching this. Alright. Ownership and drop show up in a very real way. Temp artifact is one of the strongest Rust teaching examples in the whole code base. It owns the temporary output file and cleans it up automatically unless it gets committed. Here's an example of the code. So we have a path buff, committed bool. So that's true or false, whether it's committed or not. And then it goes on to create a commit function, passes some parameters to that function, pretty similar to other programming languages. So if you're familiar with Python or C++ or even JavaScript, I guess this is going to be fairly similar. It's an object-oriented kind of structure, or maybe it's something different. I don't know. Don't quote me on that. All right, so moving on. Database.rs. Now the database layer makes the pipeline resumable. Let's see. All right. So what the database functions do: claim next job selects a row and assigns it to a worker. Checkpoint start records that a stage has begun. Checkpoint complete records that a stage is finished. Set SHA if missing preserves an existing hash through coalesce. Set output path stores a final artifact path. Mark failed records errors and releases locks. Mark done and release finalizes the row and clears worker ownership. And why does this matter? Well, Rust gives type safety and memory safety, but the recovery story here comes from explicit persisted state transitions. That is what lets the program survive crashes without losing track of reality. Here you can see there's an SQL schema, kind of little example of the code. System treats SQLite as a source of truth for state, lock ownership, and progress and recovery decisions. All right. Now we have come to the watcher thread. Is practical Rust concurrency. As an example of the watcher thread code, I'm not going to read it all out loud, but it's basically creating a mutable watcher variable. So this mute means that the variable might change at some point, and it's going to return results based on the event that occurs in this function. And it's okay. So down here we can see it's creating a hash map, and it's going to check the path buffer, and if it doesn't exist, it's going to be like, all right, create a new hash map, debounce. And then we have a duration, so it doesn't just keep running forever. It's going to debounce for a certain amount of time, and that will keep it from creating a forever loop. So the code receives watcher events through an MPSC channel instead of tight pulling loops. A hashmath path buff instant filters out repeated modify events so the same file is not spam and queued. Now the watch loop lives in its own thread and hands discovered files back to the database-backed pipeline. And then this brings us to error.rs. So this is our error crate. Layered errors keep module boundaries clean. And so we have an enum. And so it's basically a blank data container. And this is going to describe what the pipeline error is going to do for us, basically, essentially. So it's going to take DB from the crate database, the database crate, file system ops crate, input output error crate. That's from the standard library, as you can see right here. And some other stuff, watch and fail point. And so this is a good place to explain this error and hashtag from the whatever that is. All right, lower level module errors can bubble into a higher level pipeline error cleanly so the rest of the application stays readable. All right, this brings us to the closer. I'm talking for about 25 minutes about this. And like I said, the code's on GitHub. I'm just trying to create a quick explanation and try to explain this Rust code so that there is a method to the madness, but there's also comments in the code as well. And so why this code is such a good Rust teaching example. Now state is visible, queued, processing, failed, done, and all intermediate steps are encoded directly in types and persisted state. Now safety, cleanup is automatic. Temp artifact ties temp file cleanup to ownership so you do not rely on fragile cleanup calls. And recovery is engineered. The pipeline records transitions, releases stale locks, recognizes completed outputs, and resumes from meaningful checkpoints. Now, takeaway for all this. Rust concepts stop feeling abstract when they are clearly solving correctness problems in a real system. All right. So, yep, that's basically I made this little website so I could explain all this code, and also showed you some of the code as well. And now one thing we haven't done yet, let's actually build the project. So now I'm assuming you have cargo, or if you have Rust on your system, you should have cargo. So if you have all that installed already, I'm just going to type cargo build. And this is what it's going to look like when you, if you were to build this project on your own system or inside a VM or wherever, you're running your Rust. All right, so it's going to download a bunch of crates, all of our dependencies that are in our .toml, cargo.toml file. It's going to download all these and the correct versions. And then it's going to build all those and link all of them together for us. And then after this is done, which shouldn't take too long for us, or for me at least. All right, now that that's done, I can just type cargo run. All right, cargo run into our terminal. And now as you can see, our program is running in the terminal. Since we didn't create a GUI, it's just running in the terminal. And as you can see, we have in our file our box over here, we have inbox and outbox. So what I'm going to do, I'm going to copy all this code into our inbox, just as an example. So once some files hit your inbox, it's going to automatically, as you can see here from the terminal, it compresses it, copies it, or copies it, moves it, compresses it, and then it records that in the database as well. And let's see if I can access our database. Don't worry about that. Let me set this up real quick. All right. Now let me pull out SQLite 3. And then let's see. Oh. Okay, well, basically use SQLite 3 to access your database. I've already been talking for 30 minutes, but that's probably enough for this video. Now basically, there you have it. And so as you can see, pipeline complete, gives you a little output message. Probably clean this up a little bit, the output. I just did this for an example. But as you can see, it automatically copies all your files, compresses them, and then it stores it into a SQLite database, which is a SQLite is just a local database stored on your machine. But I could change all that in the code, so I'm going to go and Control-C out of this and clear that. Boom. All right. Nope. That's it. That's all, folks. Like I said, the code will be on GitHub. And like and subscribe for more content like this. All right. That's all, folks.